Hello, everyone. Thanks for joining in. Welcome for this session by Robert on concurrency-oriented programming in a modern world. So we are glad that Robert could have some time for us today. So over to you, Robert.
Hello. So yes, now I'll just start sharing my screen here. So hi. So I'm going to talk about a bit about concurrency-oriented programming in a modern world. Yes, well, and as an example of this, we'll be given a lot of what we were doing when we were developing and using Erlang and how it's gone on and how it relates to things, different ways of doing the concurrency and the sharing, things like this as well. So yeah, I was a physicist originally. Now we're talking 40 years ago. And I started working discovered programming and started working for Ericsson. Yeah, let's see, we go there. Yes, I just put up one thing here and then we're done. Right, got my laser pointer here. Yeah, so this is actually me at work. Okay, so my name is Robert Virding. I'm one of the co-inventors of Erlang. If you've seen things like Erlang the movie, you will have seen me there as well too. And I just like experimenting and well, tinkling with things and doing things like this as well. And this is actually me at work because for a trade show, we wanted something to demonstrate Erlang. Was doing this and just doing telecoms type stuff. You would just have this was our little business exchange we had in the lab so we could test things, and just showing this wouldn't attract many people. So we came up with the idea we would have an electric train system, and it would have been an ATC, automatic train control system, written in Erlang for controlling the train and keeping tracks of this. I probably went slightly overboard here for it because we did a lot of stuff here as well too. But yes, it was good because the train control system, it was written in Erlang, which suited very well because each train had a process and things like that. Lots of processes managing and kept track of where the trains were and made sure there were no collisions or anything like this as well too. Let's see, I have a chat popped up here. Things disappear there. Yeah. It is. This wasn't the train system we were using for the demo, but this was me experimenting and building things, testing all the ideas. But it was very good. And it was just a very simple little thing and just attracted people. So it was, in that sense, it was a very good tool. So yeah, where are we? Yeah. So what we were talking about. So I was a member of the computer science lab. Ericsson had a computer science lab. And we had a number of things to do, just amongst other things, looking at new technology. But one of the things we were looking at was how we could help Ericsson in the way they were developing and maintaining their telecom system. So they had a very good system called the AXE, which was one of the very early electronic systems for telephone exchanges, and it worked very well. But of course, you can always make things better and have new ideas for it. And this is one of the problems we were looking at in the computer science lab. We're doing other things like this one. And what you find is that you have to understand the problem. What was the problem, and how we could do this? So it just wasn't wild experimenting. We had a target for doing this, and this was how you could help program on one of these telephone exchanges. That's why we had the small little exchange that I showed up here. This was what we were experimenting with. And we did a large number of experiments. We had connected our computer to it. We had a VAX running Unix. We connected to it so we could do a lot of experimenting with existing languages. So what we found was that none of the systems we could run on our machine were very good at this. So we had to try and understand what was going on. And what we're thinking is, okay, developing a suitable language. And there's a lot of concurrency in here in the system. What was it all about? And there's a very hard requirement for things being fault tolerant. The exchange could never go down. I mean, you could lose calls, yes, but the exchange must never go down. So it had a lot of fault tolerance. We also had the requirement that you're able to do live software upgrades of the system while it's running. And the thing was, what does all this mean? What does concurrency mean? Are we talking 10 things, or 100 things, or 10,000, or 100,000 things? And how is the fault tolerant? If something goes wrong, how we should handle it? Live system upgrades, and how all this should work. And it was thinking and experimenting, which eventually led to Erlang. So we were 3 people in the lab. It was Joe Armstrong, Mike Williams, and myself were working with this. Other people in the lab were doing other things as well. And we were very fortunate in that, okay, so Joe and I, we came from the outside world. We could make a telephone call. Mike Williams, he'd done some work in developing inside Ericsson systems, so he had a certain feel for it. But we were very lucky in we could get in contact with another group in Ericsson who were going to develop, looking at prototyping a new architecture, wanted something to prototype the system. This is Joe, Mike, and me. This is from Erlang the movie, if you've seen that. Right? It's quite funny. It was very, very funny. It was. We did it very seriously, but it turned out to be quite funny. But yes, here we're sitting working, and you notice I'm the one who's doing the work, and it's Joe and Mike. They're just sitting talking on the telephone. It's a bit of a change here for it, but where we ended up with, so we had this group who could help us, and we came up with a lot of ideas of how a language should look, how it should work, how it should be used to build systems. And this group, they could come back with very good feedback to us and say when we were right, what had we got right, what had we got wrong, what had we misunderstood, what we missed, and everything like this. And this meant that the language and the way it would work evolved as we were going on. And the first project they did, it was a prototype. They did something like 10,000 lines of code, and doing this for testing their ideas, testing our language and our way of building the system, everything. So it's not just developing a language; you have to come up with how we're going to use this language. And again, it was very focused. Otherwise, it's very easy just to wander off. And again, having this type of focus, getting the right type of feedback, that's just not for language development. If you're developing a system or a library, anything like this, you need to know where you're going. This also became actually the first project, the first product Ericsson had on top of Erlang eventually. Yeah. So where did we end up? We ended up with the Erlang language. And its basic language is pretty much a standard functional language. There's nothing strange, and a lot of people think the syntax is a bit weird. Well, it can be in many ways. It's quite a simple syntax. But otherwise, it's very type of things you'll find in most functional languages. There's pattern matching, for example. We have immutability of data, for example. We've got things like the tail call optimization, so you can write recursive loops and everything like this for it. Again, there were no loop statements in, but so how you do it, just write recursive calls. But this is where it was getting interesting. We worked out, and we felt that this was going to be used in the type of application where you have lots of concurrency and lots of error handling. So we felt instead of the best way to do this was to put the basic primitives into the language itself, not just in an environment. We felt these were so fundamental to the problem, we put these in there at a very early stage from the beginning. So if you look in the language, you'll find there are primitives for creating processes and communicating and catching errors and everything like this. How you then use it, that is you can do in your environment here. You can make a set of tools building these things. So we delivered both the language and the environment around which you could use it, which they could then build their application on. And they, as I said, they were very happy with it. It's quite funny getting the feedback because they would tell us that this was a good idea, this was a bad idea. Well, this was the best one. So this was a very good idea, but we can't use it. That means we just misunderstood the problem. And we also found out it was much better for us not to provide solutions, but provide tools for them to build a solution on top to get for it. And this was just a general feeling for it. Now, the language input into the Erlang language, it came from a lot of different places. So we were looking at concurrency and other things here. We can see, for example, in Smalltalk and Ada, they had this. We looked at other functional languages. We looked at logical languages. The original system was actually written in Prolog and then migrated to being a functional language, and we're adding the concurrency primitives for it. And these came in, this is what eventually became Erlang and the environment around it, which is called. It's gone another step. There's another language which has become very, very popular, very used, called Elixir, which is built on top of Erlang, which has all these features, but it's got other things put into it, libraries. It's had the syntax and things like this. So the whole thing has been developing in the same way. And again, it's for attacking a similar type of problems. And what we did find was that where we'd been concentrating to one thing, this type of system, the properties of the things you want in the system are much more general than we had realized from the beginning. So I mean, well, apart from the ATC system at the end, I mean, someone developed a system in Erlang for doing web servers, and I thought, well, why would anyone want to write a web server in Erlang? And then you start thinking about it, and you want the same type of thing. I want to be able to handle lots of connections. I want to make sure that the system doesn't crash. Things will go wrong. I want to be able to handle that in a nice way. So the problem was much more general. And this is Joe. This is Joe Armstrong. And this was later from a talk he was giving at an MIT workshop in 2002. The language development was around 1990, 1991. This came later for it. But he came up with the term concurrency-oriented programming. And his basic tenets here were that if you look around, the world is concurrent. Things in the world don't share data. Things communicate with messages and things will fail. And this talk, a talk like this is an extremely good example because we've got lots of things going on at the same time. Me giving the talk, you listening to it and seeing things. We're not sharing data. I'm sending you data. I'm communicating with messages. In this case, I'm sending pictures and sound and things like this. We're communicating. And things can go wrong. The net can go down or your machine can crash, or hopefully my machine won't crash, but it could, and things like this. So these are the basic tenets in what Joe called the concurrency-oriented programming. And this is what we were doing. We hadn't thought about it this way at all. But yes, if you find that. And if you find that, look at the type of systems Erlang and Elixir being used today. They're very different, but they have these basic ideas of what's in the system. And this is slightly wandering, but it's a bit funny. Yeah. So this is a quote by Alan Kay. So he said, object-oriented program to me, it just means only messaging, local retention and protection, and hiding of state processes, and extreme late binding of all things. Which, when you think about it, this is pretty much what Erlang is done. We didn't have this talk, this thing there, but this is pretty much what it's done. And Joe made a quote on this. He said, Erlang might be the only object-oriented language, but it's based on message passing. You have isolation between objects and you have polymorphism. So he was saying Erlang was the only really object-oriented language. Not everyone agrees, of course. And it's pointing out that not all object-oriented languages do follow this principle. Well, as Alan Kay once said it, inheritance came later. So what is this about concurrency? What do we mean by concurrency? And here we're relating it also to parallelism, because sometimes you're talking both about concurrency and about parallelism, and how do you separate these? How do they mean different things? And so, because sometimes you will see that people are talking about concurrency and they're talking about parallelism at the same time, or the other way around the mixing. So what we see here, this is not just our view here, Rob Pike, concurrency is about dealing with lots of things at once, and parallelism is about doing lots of things at once. So you can have a concurrent system where you're running 100,000 different things at the same time, but you might only be running on 10 processes. So the difference here, so as we see it here, is that here's a very simple example. We've got two tasks A, we've got task B, and A consists of A1 to A2, 3, and B to B1. And you can run these concurrently. You can have one thread running bits of A, bits of B, and things like this if you're running this concurrently. Or you can have two threads here, and you've been doing these in parallel. But they still don't describe this. They still have the same system, just how you're. And I have one view is that concurrency, that's a property of the problem you're looking at and your solution to the problem. Whereas parallelism, that's a property of the system you're running it on. Okay, so I can make my concurrent system for running 100,000 different things, but I can run it on something on one processor. And this is what the original systems were like this. We were doing telecom systems running on a single processor, but doing an enormous amount of things concurrently. Again, you're splitting up what's in parallelism. A typical way of showing this is, or talking about this is, you could say, yeah, we have the kitchen in a restaurant, and you can have one cook in there. That cook can be doing lots of different things at the same time, working a bit on one course, but on another, making one dish and things like this, working, and he or she is doing that concurrently. Or you can have lots of cooks in there, and you have one cook for each dish that's being prepared, and then you're running them in parallel. Just a common way of trying to show the difference of what's going on. The result will hopefully be the same. You're going to get a number of dishes coming out, but how they're being prepared is very, very varied. And how each dish is prepared doesn't change. Each dish, in this case, the A here is going to do an A1, an A2, and an A3 because that's what's necessary with how you're doing it. I think it's very important to keep track of the difference between concurrency and parallelism. So you know what you're talking about and you know what you're trying to do, trying to solve. A little bit more about concurrency here. There are many ways, but talking here about handling memory and things like this, but they're basic two ways of doing it. You can have a shared memory system. You can have these two things running concurrently and they're sharing data. Or you can have no shared memory. So when the blue here communicates with the A, it can't write it in here. It has to send a message. Now, both are perfectly valid, but they have a lot of different properties. This, for example, is what common to, for example, using Go. Using Golang, you will have shared data. So one thread one process might tell the other, yeah, look here, you'll find some data I've written. And it can start sharing this data. Whereas if you go into the concurrent way here, we'll be sending messages saying, here is the data, do something with it. Now, they both are right, but they have different properties and be very much aware of what's going on here. The problem here, if you're sharing, will only work on a single machine. You can't share from different machines, because then you're actually starting to send messages. So yeah, now we're sort of slowly wandering into distribution. Distribution, that's what you're abstracting away from where, in one sense, you're abstracting away from where things are being done. Right. So we can do a lot of things spread out. For example, we might have one doing one thing over here in Bangalore in India. We can do other things in Africa, or they can do good. So they will be communicating with each other. And yes, it can slow things down, because I have to send a message to other places in the country, other countries in the world, other machines for doing stuff like this. But it does, if you're doing things in parallel, it can speed it up. You're adding scale and resilience to the system, because if one of this machine's going down, if that crashes, the other ones will still keep going and doing things. If you're sharing the data in the right way, they can handle this for it. This actually is what happens when you're running multi-core. Okay. You can have lots of cores on the chip, but cores can fail. And if you've got immutable state and you're not sharing, then the system can handle the cores failing. Like they can handle something like this, where a machine goes down. So yeah, concurrency and distribution. So what we're talking about here is we have immutability that we're using in concurrency, which we can then use for distribution. And from one point of view, you mightn't see the difference between the concurrency and the distribution when you're running the system, because I'm just sending a message to that. If that message happens to be on my machine, happens to be somewhere else, I don't necessarily have to see it. And distribution gives you parallelism. And at the same time, if I've got multi-core, I also have parallelism. So there's just two different ways of getting to the same thing about parallelism. The thing to remember is, yeah, parallelism is good for many things, but it can't give you infinite speed. You have Amdahl's law here, sort of limiting this. The time taken to do something will be the time taken for the longest piece to do it. Right? I might spread things out over in 10,000 machines, but if there's one thing that takes 5 seconds, it's going to take 5 seconds the whole way. So yeah, that is just to be aware of what is going on here when you're doing things. Yeah. So even when you're running multi-core, you are actually doing things in parallel. Yes, you can actually share data between the cores, but then you're running into the same problems as we were seeing here. That if something goes wrong here, if one of these processes, concurrent things, crashes, it can ruin the data for the other one because they're sharing. I mean, in this case, the blue might crash while it's updating data for the red, and the data will just be a mess. So you can do multi-core, but to get the best out of multi-core, you need to do, you need not to stop sharing when we're doing immutable data and passing things around with messages and stuff like this. This gives you scalability and reliability. Okay, the multi-core does as well up to a certain limit. I mean, someone can pull the power out for that whole machine, and all the cores go. But this gives you scalability and reliability. This is something you really want for doing systems that are critical or always need to be running. And what we also found from the very beginning is that for reliability, you need at least 2 computers. You cannot make a completely reliable system on one machine, one computer. That computer can go down, everything goes down. And that's why we in the Erlang language, if you look at it, we both have the primitives for doing the concurrency and the error handling, so we can build these reliable systems. But there's also primitives for doing distribution, so we have support for doing reliable systems in a distributed way. And what we also found from the very beginning, which I mentioned earlier, these things are so fundamental, these properties, you don't bolt them on afterwards. You can't take your sequential mutable language and say, I want to run this in parallel or concurrently and in a safe way, because it just doesn't work. You will end up trying to do the same thing. This here is from an interesting panel discussion. It was held by Francesco Cesarini here about this, and we had Carl Hjort here coming. He was the person behind one of the people behind the actor model. We had Tony Hoare here, who was working on multiple transputers and multiple systems, and we had Joe here, which came from us in the Erlang style concurrency. And they were discussing this for it, and they were talking about the problems they were trying to solve. And where we found found out in this discussion was they all pretty much ended up in the same thing, right? We ended up using the actor model. And the actor model, that is doing things independently of each other, communicating with messages and things like this. I can just point out now that when we were developing in the early 90s, the actor model had been around there for a while. We were not aware of this. We arrived at the actor model because we found there was something that was very good for solving our problem. This is how we want to do that. Okay. And actually, I met Carl Hewitt much later. This was 2019, before COVID, we could still go meeting people. And I was talking with him about this, and I said I was a bit ashamed. And I said, well, we're a bit ashamed because we hadn't heard about the actor model. And he actually saw this as a benefit, something good, because they had arrived at the actor model from a very theoretical point of view, whereas we had come from an extremely pragmatic point of view. This was just something, a good way of solving the type of problems we were looking at. So he saw this as a strength of the model because it applied both from the theoretical and from the pragmatic views of getting what they saw. So that was a very interesting discussion for us as well too. And of course, why is this relevant today? Well, this in many ways is pretty self-evident. So today's systems, they are most of them extremely distributed. You've got mobile, you've got clouds, you've got clouds here, you've got the Google clouds, you've got the Amazon clouds. You've got things like Zoom we're talking today, which is an extremely distributed concurrent system. So I'm running Zoom on my machine, talking with your Zoom running all machines. The whole thing works because it is concurrent, because it's distributed, and we're sending messages backwards. You have things like WhatsApp, which again is an extremely concurrent system. I can just boast a bit here. I haven't taken part in developing it, but the WhatsApp backends are written in Erlang. And they're using the Erlang features for the concurrency, for the fault tolerance, and all these things we've got into the system. Again, and they're doing an extremely parallel work. Back in the old days, they only had a few machines running, but now they've got hundreds of thousands of machines running, and they're all working together doing this extremely concurrent parallel. Another one, a similar one here is Discord. Which also works in the same way. It's like similar to Slack, and we're talking things going on, and Slack's running, and it's running on different machines, and talking with each other. It's actually written in C, a large portion of it, but it's doing exactly the same thing. We have parallel computer games. Getting back to Ericsson, a large part of their mobile systems are written in Erlang, but they are extremely concurrent for doing this. When they're doing this. We have banks, an OTP bank here. We've got bank backends and things like this. So this type of system today is extremely relevant. There's a lot of things going on about it. And they work because they're not sharing data. It's all message passing. So if one of the machine dies in your bank, for example, in your bank backend, if one machine dies, the other ones will be able to keep up because they know what's being going on. It's sharing of data between them, so that all the data is not local, and they can handle these types of crashes going on. And when I'm saying sharing the data here, I mean they're sharing data in the sense they're sending the data backwards and forwards in messages, like using shared memory for it. Or they can have a database at the back end where they're sending their data backwards and forwards. And that database can be distributed in parallel to keep track of things, both as your amount of data and to make sure that data is not lost. So you can add a lot of things down. And again, as I said, multi-core, that is actually doing things in parallel. So you can get a lot of the features here for it. So if your system is designed in the right way, when you can run your system on one processor with about 10 cores, and then you can just shift it over to one with 50 cores. And you don't have to do anything because you're using the concurrency and the inbuilt concurrency and the parallelism in the system to do this for you. And this is how Erlang works internally. In the virtual machine, it just does all these things. I got my processes, I'm sending data backwards and forwards of processes. And which core that process happens to be, that's totally irrelevant from my point of view. But the virtual machine inside keeps track of it. And if I'm sending to a process on another node, that also can be completely irrelevant to me. There is explicit support for doing it, but there's also a lot of the things that you'll find in Erlang for the concurrency and the error handling work completely well on a parallel system doing. Again, it's just thinking about these things from the very, very beginning and working it out. And I can just say and stress again that you have to, when you're attacking your problem, in our case, it was developing a language and a system, but it might be something else there. You have to be very careful and keep track of what is the actual problem you're trying to solve. Where do you want to go? What is important for this system? What isn't important? Things like this work. And I can just say from private personal experience, it's very easy to wander off and do something else. And if you're not careful about it, and just lose track of where you're going and what you're supposed to be doing and things like this as well too. Yeah, that's that so far. And again, yeah. So again, we see this a lot today with distribution in the system. And now, for example, we can often have support, help for doing things. For example, we can run Kubernetes for doing our distribution and keeping track of sending things and setting stuff up for it. Again, it works if you've designed your system in such a way. If I've designed a system that can only work on one machine, it doesn't matter if I've got Kubernetes and running docs, things like this for it. It just doesn't help. I again have to design my system to do this so I can use that. And so Kubernetes, that keeps track of everything, and I've got Docker for handling each container and talking things between them. But again, we've still got this whole thing with doing things in parallel and distributed systems for it. And this again is very fundamental today, and it's just going to get more and more as we go. Well, you know, it just is. Yeah. So what we found was that concurrency, that functional programming is done with a classical functional way, and concurrency work very well together. Okay, that's what we found. Just the functional model works very well together in a concurrency with concurrency and with distribution, distributed systems as well. It just fits in very nicely because a lot of the features in the functional language, for example, the immutability, just fits very well into everything else. And again, I want to stress the point here that when we were developing what became Erlang, we did not know this. Okay, so we weren't out to make a functional language. We weren't out to look at concurrency. Well, we had thoughts of concurrency, of course, because we knew a lot of things had to go on, but how should the concurrency look? How should the fault tolerance work? They were things we discovered as we were working on the system to get it out. Again, as I mentioned with actors, we found later that this fitted very well into the actor model. So we were doing actors, although we never thought about that. Okay. So again, be very focused on what problem you're trying to solve. And again, this is not just for doing languages, but it could be for developing an application, libraries, systems, and things like this. What you want in the system. And very often you'll be using systems where you don't see it. Your typical operating system, like I'm running on my Mac, that's doing things concurrently and in parallel. It's running on multiple cores. But if I don't know about it, I don't see it in that sense. I don't notice it in that sense. I don't think about it. This is just a shameless rip. So it's my first rule of programming. Any sufficiently complicated concurrent program in another language contains an ad hoc, informally specified, bug-ridden, slow implementation of half of Erlang. And again, yeah, it's a bit of a joke, but there's some truth in it as well too. That you will find these things again, how you did it. Again, we got there because this very much targeting this input. It's a rip-off of Greenspun's 10th rule of programming. Any sufficiently complicated C or Fortran program contains an ad hoc, informally specified, bug-ridden, slow implementation of half of Conf. And again, if you start looking, yes, it does. Yes, he was also joking there, but not quite joking. And the main point here of the whole thing here is you cannot put these things on concurrency to a language as an afterthought. You need to get it in, integrated from the very beginning, because it affects everything else when you're doing things. So you have to think about these things from the very beginning. And we were talking with Simon Peyton-Jones about the functional things, and he made us realize, although we hadn't realized it then, how much our functional programming had influenced our choices. We hadn't realized this from the very beginning. Again, I said we weren't out to make a functional language. It started off as a prologue, actually. And then we found that the logic languages, I love logic languages. I also love Lisp, just to get while we're here. But they weren't the right thing because they had properties we did not want. So we ended up by migrating from a logic language to a functional language at the same time as we were working on how the concurrency should look and how the error should look. The whole thing evolved with this. And we found that now there are a lot of functional languages coming out. Hopefully there'll be more, they'll keep going. And I know I'm not saying Erlang is the only functional language or the best functional language. It depends what you want to do with the language. But the system we were looking at, it was what was good. For example, I mean, some people complain, and they're perfectly right. Why don't we have a static type system? What's wrong with static type systems? And I'll say static type systems are great. No, just as long as I don't make them too complex, but they're fantastic. But from our point of view, we could not put that in because we had this requirement. We had to be able to upgrade the system while the system was running. And that means having things like global types in the system just don't work. I can't change the type of something here, some data structure here or some functions here, and have these in another module, another part of the system calling it. It just doesn't work. You can't change things like this. And typically, if you're having static typing, it's global for the whole system. And these are just things we found, which meant we couldn't add them in. And this is not because we thought static typing was bad. It just was. It just didn't fit in to what we were doing. Yeah, that's what we're getting onto there. And that's about it. Well, I can keep on talking for as long as you like. There's no problem. But yes, so that's mainly what I wanted to go through. And if you have questions, please you can take them up now. We still have some time, or we can go on later into the meetup.
Thank you, Robert, for the insightful session. I see Mahir has raised hand.
I see one question. I can take it while now. Is the closure on Erlang fully developed? You mean the closure language? There is one. I haven't worked with that. Closure and Erlang don't quite really fit. Well, they're not the same thing. They do things slightly differently in how they handle concurrency and stuff like this. But there is a closure system. There's a couple of them actually. I haven't tested them for it, but yeah. So on that, I can't help you.
And Robert, thank you so much for your time. Let's connect in the Hangouts.
Yeah, you're welcome. Ned, come to the Hangout and talk about Akka. Yes. Okay. Goodbye.
Okay.
Thank you.
Thank you, everyone.